Welcome on this ConSteel webinar. The topic will be today plastic analysis and design of framed structures. Let me introduce myself. My name is József Szalai. I am the Technical Director of ConSteel Solutions Limited, the developer company behind ConSteel software products. First of all, some practical notes on how to use this webinar tool. You can hide the panel just hitting this button with the red arrow, and you can ask question after the webinar using this chat box area, and I will answer it. This webinar is part of the fall webinar series, actually the last one, and the previous webinars were about composite design, composite column and composite beam according to Eurocode, and those can be seen on our YouTube channel who is interested. And today we will discuss plastic analysis and design, also according to the Eurocode standard. About the content, briefly, first, the plastic analysis tools will be discussed in ConSteel, how to handle plastic hinges, how to define them, what are the limits, how to define the behavior of these plastic hinges. Then I will review the possibilities of plastic hinge analysis in ConSteel, first order results, second order plastic hinge analysis results, and plastic stability calculations. And then I will review plastic hinge design based on the stable length approach of Eurocode 3. This is a function coming in the next version of ConSteel 10, which will be released the beginning of the next year. So let me start the presentation with a framed model, a 2-bay hinged frame structure. The structure composed of hot-rolled elements, AGA cross-sections for the columns and IP cross-sections for the beams and hunches. And I applied the usual bracing configuration which is needed in ConSteel. In any time we would like to calculate the in-plane behavior as well the out-of-plane behavior, so the out-of-plane buckling behavior mainly. So now I defined some supports on the top flange and some rotational restraint at the end of the hunch, and both on the column and both on the beam as well. So this is the model. I applied just some loads and horizontal load as well, and also an initial sway is taken to this frame. So first of all, let me show you the behavior of this frame as it is now elastically, just to see the difference. So first I choose the elastic calculation, first and second order, and buckling analysis calculations. I run the analysis. What we see is some deformation. We can check the bending moment diagrams, and we can see the buckling behavior of this frame. What we see is that the dominant buckling mode is lateral torsional buckling of the beams just around this end position of the hinge, where we have the complete support at this cross section. We can see this two wave-like buckling shape. So this is the dominant buckling mode at a critical load level equal to 3.72. We can seek for other modes, and we can see that the swaying mode, the swaying buckling mode, the critical load level for this buckling mode is about 4.15. So quite low. The structure is quite slender and quite sensitive to second order effects in plane because of this in-plane stability. If we see the global check elastically, both cross-section check and buckling stability check, then we can see that the structure is not adequate. The maximum utilization comes from global stability resistance, and of course around this region where we have the highest bending utilization and where we have the most dangerous buckling mode from the calculations. These calculations are done by the general stability resistance calculation of Eurocode based on the elastic critical load levels. So we have a not adequate segment in our column and in our beams as well, here, here, and here. And if we see only the plastic resistances, even the plastic cross-section check, we see that those are not adequate. Of course, those are higher than the plastic limit of the cross-section. That's why we will use the plastic analysis now. So I would like to show now the plastic analysis settings. Here we can choose the type of calculation from elastic to plastic, and if we choose plastic, we can calculate static analysis first or second order and buckling analysis as well. This is based on linear buckling calculation, including the plastic hinge effects. We have some settings for the plastic hinge analysis. First of all, we can, if we have a more complex model, we can choose just a model portion in which the program is looking for plastic hinges. So if we don't want to use plastic analysis for the whole complex model, we can choose appropriate cross sections, compact and symmetric, and we can set the condition for accuracy for the searching engine finding the plastic hinge. Then behavior of hinges, what does it mean? If we have a plastic hinge in a three-dimensional model, it can behave as a three-dimensional hinge. At the moment in ConSteel, the plastic hinge is just an in-plane plastic hinge, so it is a major axis plastic hinge due to the major axis bending moment. But if we calculate out-of-plane behavior as well, this major axis plastic hinge, if we consider that the, for example, an eye section is fully plastic, then the flanges are also in fully plastic state, then we can guess that maybe for out-of-plane buckling, out-of-plane behavior, the rotation about minor axis or the warping deformation is also plastic. So we can set these additional conditions here. Then some warnings about the normal force, minor axis bending and minor axis shear, and rotation in the plastic hinge, where to notify us in which value. So if the rotation is higher than now 6 degree, then we get a notice, warning message. And then what are the results of this plastic hinge analysis at each stages, which should be saved. So we can check out all of them, or if we don't want to see any, just the final stage, then we can take out those results. So these are the basic settings. Now I leave it in that way. This is the default settings. Usually it is quite good, and according to the Eurocode it is appropriate. Now let me show you first the first order plastic hinge analysis. So I run now the calculation and see the plastic analysis results. And what we see here, that we have 4 plastic hinges now. Here, a first one, second one, third one, and here a double plastic hinge. It is the highest bending moment here, but this is the last one, and now it became a plastic mechanism. So this is the final stage now. What we see that at the first order stage, so at the load level of 1 equal to 1, which is the design load level, we have only one plastic hinge that below 1. That means that at the design load level we have to calculate only by one plastic hinge. So this is the only plastic hinge for which we design our structure. It is very important to see that in ConSteel the design method is always not a final stage. So at the yielding mechanism, the fully plastic state. So the design is not done at the 4th stage, but always the design loads are calculated, and we see what is the state at the design loads, how many plastic hinges we have under this design load level. Now we have 1. If we, for example, put out the initial sway, then it can happen that at this load level, even if it is a plastic calculation, a plastic analysis, we do not have any plastic hinge first order calculation, because if we see the plastic hinge history, we can see now that even the first plastic hinge is just above the design load level. So it is 1.002. The second one is here, somewhat different as earlier, because of we neglected the initial sway now. So in this case, the design is completely the same if we have an elastic design, because at the design load level we have a purely elastic state of our model. So in the design we do not have to use the stable length approach, just using the reduction factors for stability. And of course the backlink results are also calculated always at the design load level. So in this case, if at the design load level we have an elastic state, the backlink results are also the same. We have the same in-plane backlink mode at the load level of 4.15. So it is very important to see these were the first order results because I would like to show you that what are the differences if we switch to second order, which is quite important in case of a slender structure like this. So now I calculate this plastic analysis but using the second order option and the buckling as well. I run the analysis, and what we see, if we see the plastic hinges, the plastic hinge history, that we have 3 plastic hinges below the design load level, so below 1. So the first one is 0.967, 0.978 and 0.987. That means that at the design load level now we have a plastic part of our model, and this is because of the second order effect. So the second order effect created now a different situation at the design load level. If we see, and also only the 4th plastic hinge, the last one, now which is above the design load level, so the above 1. There can be a question that earlier we had 6 plastic hinges, now we have only 4 plastic hinges. What are the reasons? Maybe what is the reason for that? The reason is the second order behavior now, which is taken into account. In first order analysis, between the plastic hinges, only first order elastic incremental calculations are done, including the hinge effect. But in second order, we always perform a second order calculation which includes the actual reduction in stiffness due to the second order effect. And in this model, since it is a very slender model, these second order effects, when we reached the 4th plastic hinge, the second order effects made this structure unstable. How can we see this? If we look at the buckling results, what we see is that we have a different buckling shape now, which is dominant. This is the in-plane buckling, but considering the 3 plastic hinges which are relevant below the design load levels. And if we have these 3 hinges, or the stiffness, the in-plane stiffness of our frames has a much reduction. Now due to these 3 hinges, and that's why we can see the value here drop down from I don't know, it was 4.15 to 1.58. This is a very, very low value for critical load level. That means that in this state our structure is even more sensitive to in-plane second order effect, and this is because of the relevant plastic hinges at the design load level. And we can see also the second order results including these hinges. So we have now 3 hinges at the design load level, and it is of course taken into account when we see the bending moment or any kind of internal force calculation. So this part was about plastic hinge analysis in ConSteel briefly. There was earlier another webinar fully on this topic. It was just a brief summary of the capability and the results, and I wanted to stress the difference between the first order and second order plastic hinge analysis, because usually when we use plastic analysis, usually the strategy is that we would like to see as slender elements as we could, and then out of plane we use a lot of points to stabilize the out of plane buckling, but in plane we usually do not have any chance to stabilize for stabilization. So in plane these very slender structures can have a very low critical load level for in-plane swaying buckling mode, and that causes a very important second order effect in our structure. So I wanted to stress this and the possibility in ConSteel to treat this. And not only calculating the second order, it is very important that we always can see the buckling results, so visually and quantitatively can calculate what is the critical value, what is the relevant buckling form if we use a second order plastic hinge analysis. And also if we see there are other buckling modes, for example including the plastic hinge, this is the first out of plane lateral torsional buckling mode of our member here. This is again just a visualization of our of the behavior, buckling behavior of our frame, of our model at the design load level, including the relevant plastic hinges. So let me go on and show you the plastic design tools of ConSteel, which are, as I said, coming in the next version. So I go to the global check again, and first of all I would like to run again the analysis, but including initial sway, because just take this design method as a complete. Considering this sway has something effect on the behavior, but not really not very relevant, because we have already this horizontal force as well, and we saw that even this horizontal force made a quite huge second order effect. So now I would like to run the design. We do not have to set any value or something for the design. We just have to check cross-section check and check the buckling check tab. There are some settings. These are mainly for the elastic buckling check, so the parts which are still in an elastic state are checked using this general method. We have another webinar on that topic. I don't want to go into the details of this part, but rather show you the plastic stable length analysis. So I run the design calculation, and we see that in the calculations we have a new one. So we have the usual results for elastic pure resistances, plastic interaction where relevant, conservative interaction resistance, global stability resistance based on the elastic rules of Eurocode, and there is a new one, the plastic stable length check, and these are only done at the around the plastic hinge. Now we have a plastic hinge here, here and here in the column, here in the beams. So we have a stable length check at the column and in these two beams. The stable length check, just shortly some word about it according to the Eurocode. It is defined at the BB3 annex of the Eurocode, stable length of segments containing plastic hinges for out-of-plane buckling. The method itself came from the British standard In UK they use this method quite a long time. They have huge tradition of plastic design, and basically the latest method defined in the British standard was taken into the Eurocode. It is quite the same, only the notations are different. These are now Eurocode notations. So about the method, basically we have to calculate two types of stable length. The first is stable length between adjacent lateral restraints. It is called LM. This is the formula of it. And the second one is a stable length between torsional restraints. And there are some modifications if we would like to calculate these restraints on hinged or tapered members. So these are the stable length. And what is the design philosophy? We have, for example, a structure like this. This is the beam or column. This is quite similar as I built in ConSteel. And we have lateral restraints provided by the side rails in this column or purlins on the beam. So these are lateral restraints, but at the tension flange only. So eccentric lateral restraints at the tension flange at this region where we have the outer flange tensioned. And at some positions we can have inner flange restraints as well, so compression flange restraint, and this restraint cross section this is a torsional restraint as well. And we have to check around the plastic hinges. For example, here we have to check these two segments for LM, so this is between adjacent lateral restraints. This is for hinged formula, and this is for uniform member formula. And we have to check also the whole segment between the plastic hinge and the first torsional restraint as well. And this is this LS value here for uniform segment and here for tapered or hinged segment. So two types of checks should be done in both sides of the plastic hinge. Of course, at the position of the plastic hinge, there are special requirements for the restraints. We should have both flange restraints. Of course, this is the minimum. So this is the basic design procedure, and this is has been implemented into ConSteel now. So this is a test version now, what I show you, but now it is working quite well, and we will release it at the beginning of next year in the new version of ConSteel. So here we have, let me start with this beam. Here we have the plastic hinge, as we remember. Here we see we have the plastic hinge here. So we have to go in that way, and the column is the first rotational restraint, and inside this this length we have no further lateral restraint at the top flange. And going in that way we have this point which is considered as torsionally restrained, and we have some additional lateral restraints at the top flange, as we can see in our structure model as well, provided by the purlins. So this is now the bracing situation of our beam. So we can see now here the utilization. Now in this segment of the beam, the utilization is 173%, and we can see the detailed calculation of this uniform cross-section. And what we see, we have the usual design results, and here we have the stable length. First, stable length between lateral restraints. So this is between the adjacent lateral restraints for uniform member segments. This is the applied formula. We can see it from the standard, and what we can see that the calculated LM, stable length, is larger than the length between the restraints, so the unbraced length, which is now 1.6 meters, and this is adequate now. So between the adjacent lateral restraints to the tension flange, we have an adequate situation. The LM is larger than the unbraced length. But what is the situation between the torsional restraints? The calculated LS, stable length, is 4.59 meters, which is lower than the length between the torsional restraints, which is practically the whole length from the end of the hinge. And this is almost 8 meters. So we have a not adequate situation now. That is what we see now. The utilization is not good, or unbraced length, so the length between the restraints, are much larger than the limiting stable length here. So this is for our uniform member of our beam. What is the situation for our hinge? We have the two stable length calculation here again. This is our hinge section somewhere, and we can see that the situation is different. Now the stable length between lateral restraints are not adequate. The stable length is quite low, it is 0.71, and the length of the hinge is 2.04. That means that the length is much larger than the limiting stable length between lateral restraints, and since we do not have any internal lateral restraints in our hinge region, then it is not adequate. But for torsional situation, it is fully adequate. The utilization is 90%, because again the length between the restraints, so practically the whole length of the hinge, is now low, has a lower value than the stable length between the torsional restraints. So it is adequate now. That is what are the conclusions for our beam. We have to put somewhere here inside this region restraint to the tension flange, and we have to put somewhere here, for example to here, restraint to the bottom flange, in order to decrease the unbraced length between the torsional segments. So this is for the beams. It is the same for the other beam. And what is the situation for our column? At the moment, our column from this point to the support is fully unrestrained, so we do not have a lateral restraint or torsional restraint. So the situation is that is the same as for the hinged segment. The stable length between lateral restraints is not adequate. The unbraced length is the whole length of the column, but the stable length is lower. So we have to put a lateral restraint, at least consider one outer point, a side rail or something on the tension flange. But for torsional situation, it is adequate. So the torsional length is much larger than the length of the column, so we don't have to put any internal torsional restraint in our column. So this is the situation for stable length. So let me do these operations now. So first of all, the beams. I have to put a restraint to the bottom flange at this point, for example, and then that will be the unbraced point for torsional torsional check, and that will be fully adequate now. So I put this Y direction, so this is the out of plane direction support, and I would like to put it to the bottom flange. Okay, and put here as well, and here and here as well. Okay, so we now solve the uniform segment, and we have to put somewhere here tension flange restraint to the top flange. So now I have to choose the top flange here. Okay, and let me say that we put it to a distance 1 meter and 1.3 meters from this end. Here, 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 and here. So we have here quite close to the plastic hinge, we have an additional lateral restraint at the tension flange, and we have left the column. We have to put again, yes, to the top flange, and let me put it somewhere here, yeah, in the middle point, here and here as well. So now I have taken in the right positions the additional restraints required by the stable length check, and now I run again the analysis. Of course, the in-plane results are not modified by this additional restraints, because those are only acting out of plane. But if we see, for example, not the in-plane but the out-of-plane buckling results, we can see that those are now a little bit different. So now the dominant out-of-plane buckling mode is a buckling of this internal column, because it is fully unrestrained. And only at a higher level we see some out-of-plane buckling of this corner region. So let me see the checks according to the stable length approach. Again, I run again the design, and what we see now that everything is adequate. We can see that the utilization is completely 100% because of the plastic hinge based on the plastic interaction resistance at the 3 positions of our plastic hinge. So here at the end of our column, here and here. And if we see the stable length check, now we can see that the stable length check is not valid for that segment, because now we closed with complete rotational restraint by putting here this additional bottom flange restraint. So the stable length is now checked only until that restraint. And if we see the results, we can see that it was adequate earlier as well between the lateral supports, but now it is of course adequate between the torsional supports as well. And the same situation for the hinge, adequate between the torsional and also adequate between the lateral restraints. It is the same here and the same in the column. Plastic stable length, it is adequate for torsional mode and lateral mode as well. And of course, for stability, the rest of the elements are checked using the elastic method, the global stability resistance, and we can see that it is also everywhere we see it is adequate, the calculation. So that was what I wanted to show you in this brief presentation about the stable length approach, together with some of the plastic hinge analysis possibilities in ConSteel. I would like to thank you for the participation on this webinar. I hope it was useful for you, and I hope that this function will be a good helping tool during your design work with ConSteel, or those who has not ConSteel yet. I hope that it was an interesting demonstration of ConSteel abilities in plastic analysis and design. So thank you for your participation, and goodbye.